Okay, so welcome. I am going to talk today about two exemplary research and development projects that we have been doing here at DBFZ for the development of biorefineries. So it is not yet really a commercial application of biorefineries, but I will talk about how we try to ensure that the results that we are making can be used nonetheless. So maybe somebody's microphone is still on. I think it's Cecilia Duarte. Is that possible? Can you please turn it off? Maybe a couple of words about DBFZ, just very quickly. So we are working on the development of processes for using biomass both energetically and in material use. And to do so, we have 5 research focus areas. These are the anaerobic processes, the bio-based products and fuels, smart biomass heat, then also catalytic emission control of this is relevant when burning biomass, and we have the big topic of systemic contribution of biomass, which Laura is working for. Today I am going to present projects that are more in the area of bio-based products and fuels and a little bit in the area of anaerobic processes. At DBFZ we are roughly 250 employees. Yes, we handle a number of projects every year, and so these are usually funded projects, but some of them are also direct cooperation with the industry. And you see the average volume of our projects just to get a rough idea. I'm head of the working group Separation Technologies and Process Design. Yes, we are working with 2 different sets of methods. One is all of the experimental methods where we are working on downstreaming of different bio-based products. To do so, we apply solid-liquid separations and liquid-liquid separations. We have in our labs, our biorefinery labs, a number of different apparatuses and technologies that we can apply. Here we're still also improving our lab, so in the next years we will really have a very, very nice biorefinery lab here at Leipzig. And the other thing that we do is we develop the concepts and the process simulations where we assess the whole biorefineries regarding their mass and energy balances and also the costs, and we prepare the mass and energy balances so that the colleagues can also do life cycle assessments. Our experimental methods we conduct usually at the scale of 1 to 100 kilograms per hour in the downstream processes. We decided to go to work in this scale because then we can still handle the amount of material that we need, but the processes are already similar to industrial processes and can be transformed to larger scales more easy. Yes, as I said, we have quite a lot of expertise in the process simulations, and these 2 topics go together quite well because in most of the biorefineries, you have a lot of separation processes that need to be simulated if you want to do a simulation. So we have the information about the separation from first hand and have these things. So this was maybe just a very, very short introduction to our work in general. What I want to talk about today are 2 projects that we have conducted in the past. One is Combustion Pro, which was about a wood-based biorefinery, and the other project is Capacity, which is a little bit similar to what we have heard just from Biofabric, but it is still a different process. It's a biorefinery based on anaerobic fermentation of wet biomass. So first to the CombiChem Pro project. The basis for this project, so maybe I have to start. We worked on this project together with the partners of a Fraunhofer Institute, Fraunhofer CBP, Center for Chemical Processes and Biotechnological Processes, something like that. Sorry about the abbreviation, but it is right very close to us here at Leipzig. They are a center where they have pilot scale facilities and for the development of biorefinery processes also, but they are larger than we are. The processes that they have, the equipment, and they have developed an organosource process during the last years, which can turn beechwood together with the protein solvent into three fractions, namely cellulose, hemicellulose, and lignin. And so they had been working on this process, and it was running quite well. And then the question arose: how can we develop fine and platform chemicals from cellulose, hemicellulose, and lignin with further processing these? And a number of products of interest were identified at the beginning of the project. Dissolving pulp from the cellulose. Then the focus was very much on the hemicellulose, what to do with this. So C5 sugar, cylonic acid, malic acid, propyl alcohol, THF, 5-HMF, furan, dicarboxylic acid, a number of different things that were looked into that we wanted to make out of the hemicellulose stream, but not only hemicellulose, but mainly hemicellulose, because other C6 sugars are in there. And from the lignin, phenols were of interest. And then in the project, we started with a large number of different lab scale developments to look into these products, how can they be produced, what has to be done. And together with Fraunhofer CBP and us, we have distributed the work so that the expertise amongst us was well used, and we had synergies in the lab scale development. So you see just some examples of the hydrothermal treatment of the hemicellulose solution, and then afterwards the different filtration experiments on how to get the treated hemicellulose solution clean. And then, very important in this project, we made at a very early stage an assessment of the processes based on the knowledge that we had at that early time. We calculated preliminary mass balances, preliminary energy balances of the different pathways that we were looking into. And then we decided which ones to follow and which ones to transfer to pilot scale. And so we took the processes from the lab scale in the upper left corner to pilot scale. In the middle, you see here the example of the hydrothermal treatment of the hemicellulose solution. And then with the results from the pilot scale experiments, we came up with concepts for the implementation of this technology. And we always looked into or asked us the question, which of these technologies can be transferred either into a process that the product and the feedstock can also be marketed, so that you can not only use it for this specific biorefinery, but also you could transfer it into a different setting. And we made boxes of concepts around our biorefinery, which we developed and assessed later on. And for those, we made final assessments, we calculated production costs and life cycle assessments and so on. So what came out of it were these blocks that we looked into. So one was, of course, the organosulfing itself in the beginning. And then we looked into pulp bleaching of the raw pulp, so the cellulose fraction, producing chemical pulp or dissolving pulp, it is called in English, I think. For the hemocellulose hydrolysate, we looked into the xylose purification to produce pure xylose, and then different fermentation pathways, for example, malic acid fermentation. For the lignin, we looked into lignin depolymerization. And for the xylose, we also looked into xylonic acid fermentation. So these were the things that we looked into mainly. And all of these boxes that you see here, we considered to be transferable also to other raw materials and biorefineries, so that it gives kind of a building block for a biorefinery. So the results in words, the conversion of beechwood into these products, dissolving pulp, xylose monomers, malic acid, cylonic acid, and phenolic base catalyzed base catalyzed depolymerization oligomers was successfully transferred from lab stage pilot scale in the project. We produced some product samples, and we were able to increase the efficiency of the organosulf process, especially the lignin recovery. And as I said, the focus was put on the valorization of the hemocellulose fraction, where a combination of adsorption, hydrothermal treatment, and nanofiltration processes resulted in 90% of the oligomeric xylose to be converted to monomeric xylose. And we calculated the cost and greenhouse gas emissions for all the products. So, and now we're have the possibility to continue with these boxes that I showed and try to go on with those, find new partners to work on these singular processes, and that's what we're actually doing at the moment. Just some further readings. I will go. You can have a look at this later on. But just if you are interested, the results have been broadly published. Yes, and this was the team. Now I think I have to hurry up a bit. But the capacity project, as I said, was on a biorefinery based on a biogas plant. So the motivation and aims of this was to turn a biogas plant off today, where biomass goes into a biogas reactor, and at least in Germany, the biogas is usually used for power generation, and the residues are extracted and used as a fertilizer. To turn this kind of biogas plant into a biorefinery of tomorrow. And we used a little bit a different approach here as Biofabrik. So they extracted their products from the biomass itself. We first apply a fermentation step, and then we extract some medium chain fatty acids from or carboxylic acids from the biogas fermentation broth. And we have done this with a couple of other organizations. So the fermentation expertise in this project comes from Helmholtz Zentrum für Umweltforschung, UFZ, which is also here in Leipzig, and we're working with them very closely. We have focused on the downstreaming, and then together with the University of Leipzig, which helped us with the downstreaming, and we had some partners from the industry that were interested in the products that we were producing here. They helped us with developing the market side, let's say, of this thing. What we did at DBFZ, we started with a fermentation broth that we got from our partners at USZ. It looks like the fermentation broth you see here, so it contains a lot of different things, still unfermented biomass and water and of course microorganisms, but also our products that we want to get out. So we have a cascade of downstreaming things that we applied here. So first we started with the filter press and the decanter to get out the solid phase and have the liquid phase remaining. Then we applied membrane filtration to the liquid phase to come out with a clear permeate, filter out the last remaining small particles and solids. And then we applied liquid extraction to the permeate because there is the possibility to efficiently extract the medium chain carboxylic acid out of the permeate. And then by a distillation we can get the pure caproic and caprylic acids, which are the acids that we were looking for here. And then similar to the project I explained before, we developed concepts for implementation. So we looked into how could an entire biorefinery look like, and we made process simulations of this to calculate mass and energy balances. We used the information that came out of this to do cost assessments, calculate the production cost. Yes, and so the main result of this was that a process for a combined material and energetic use of the biomass for the production of caproic and caprylic acid, as well as biogas and fertilizer, was developed. Maybe I didn't mention this. So the residues of this fermentation step that I explained now, they also go back to the biogas plant and can be used in the biogas process to be anaerobically digested to methane, and the leftovers can be used as a fertilizer. So the whole process chain, from just an idea to a small product volume, was demonstrated, and the product volumes were also given to the industrial partners who looked into them and tried out whether they could use them to formulate products out of it. The whole process, as I said, has a zero waste approach, so the residues go back into the biogas process, and the idea here is that also complex wet biomass can be used, so different also agricultural residues can be used as feedstock. Maybe on the fermentation, it was possible to transfer 12% of the organic dry matter into medium chain fatty acids. Yes, as I said, the rest is still available for the biogas production. And in the downstreaming, by filter press and ultrafiltration of the fermentation broth, we were able to completely remove the solids and then extract the acids with a quite high extraction efficiency so far. So maybe this can be improved in the future, but we were already, for a first project of this kind for us, we were already quite happy with the numbers we got here. Yes, and so the general benefits is that with this technology, it is there's the possibility to integrate or to make a biorefinery out of existing biogas plants and use the plant infrastructure that is already there. You just have to add on this technology and have a new product. And yes, so just a little bit what we are proud of. We got last year we were chosen for the Biogas Innovation Award at a big German Biogas Innovation Congress. So here are the two colleagues of us, Maria Braune and Heike Sträuber, who really worked most of their time on this project, and they got this nice award here. So this was the team, and I have to say thank you for your attention. This was it from my side.